Good afternoon and welcome to the fourth session on this series, Geo Processing using Python. So yesterday we discussed about in the study lecture we discussed about a prolific library or a prolific and versatile library in Python, that is NumPy, and another library for visualizing the data, that is called matplotlib. So today we will be using these two libraries as our supporting libraries for doing some basic raster data processing. Right. So as discussed in the first lecture, raster data represents objects or maybe some variables on the Earth surface as a matrix of values. Right, matrix of values in the form of pixels, cells, or grids. So any feature on the Earth surface is represented using the a matrix, right? So in the form of cells or grid or pixels. So a raster, raster is an image with a matrix of values. So those values may be representing, maybe some may represent some observed attribute, maybe the reflectance in some particular electromagnetic EM wavelength, or it may be represent some temperature, or it could be, or even it may represent the elevation of that particular point with reference to the sea level, right? So then plus a raster can have multiple bands together. So different bands can be like the electromagnetic radiation in different bands, or it may be if it is temperature, it may represent the temperature at different time intervals. Right, so this is an example of how does a raster data looks like. So here you have a cell of or a grid of cells. So here every cell might represent some observed attribute or value. So this particular cell may be reflectance in maybe red band, or it may be temperature at some particular point of time. So similar way, then raster can have multiple layers like this stacked on the top of each other. So every layer will be representing the same geographic area on the Earth's surface, but the information may be different. So every layer may represent the reflectance in different wavelengths, or it might represent temperature maybe at a different time intervals. Right. So if you see an image, the image looks like this. So all anything on the Earth's feature, so every entire thing is represented as a cell of or grid of different cells. So yeah, every cell, now if you look in, how does the, like if you see an image, we visualize the image like this, but ultimately it is stored, or a computer sees it just as a grid of numbers. Right, and the smallest unit in this smallest cell in this grid is called a pixel. Right, then raster bands. Some rasters have single band of data, while other rasters may have multiple bands together. So basically, a band is represented by a single matrix of cell values, and raster with multiple bands contain multiple spatially coincidence matrices of cell values that represent some same space. All the different layers will be representing the same spatial area, but the information may be different because all the different layers may represent information in different electromagnetic wavelengths, or as said, or it might be the temperature variability with respect to time. So there are multiple ways to represent a single band raster. Single band raster can be represented maybe either as a binary image. So image containing zeros and ones. So all zeros will be shown as black color and all ones in the white color. Or it could be a grayscale image. So grayscale image with different grayscale levels. Suppose if our image is stored in using 8-bit data, then the image will have 256 grayscale levels. So this, or the image can be or the image is a classified image, like it contains the discrete values, then the image can be even it can be represented as a color map image as well, like all the cells which have value 1 may be represented by say yellow color, all the cell with values 2 may be represented by purple color, 3 maybe some a different red color, and so on. This we can, so there are multiple ways with which we can represent a raster. So this grayscale image, or you can represent, take some other continuous color map as well, that is called pseudo color map. Then similarly, multi-band rasters, a satellite image for example has multiple bands representing different wavelengths from the ultraviolet through visible infrared portion of the electromagnetic spectrum. So all bands might be representing different information in different electromagnetic wavelengths. So and the image can be combined when we combine three bands together, and any of the band representing red, green or blue, then by combining these three bands together we create a RGB composite, or what you call colored image, or even something is called color composite. Anyway, we will see in detail later. So like this, by combining all three bands together, red, green and blue, we get a true color or natural or a colored image. So for reading and writing raster data, we will be using a library called GDAL. So GDAL stands for Geospatial Data Abstraction Library. So this is a library for raster and vector geospatial data reading and writing. So we can say that GDAL is library for reading and writing raster as well as vector data. So in the parlance of GDAL, GDAL presents a single raster band abstract data model. So there are two data, as we have seen in geospatial data. The data is represented by two models, maybe raster data model and the vector data model. Now again, and the raster data model, there are different formats. There are different. Actually, raster data is saved, stored in different formats. Maybe some at GeoTIFF or maybe IMG format or ENVI. So there are numerous formats even for storing raster data. Actually, GDAL is a versatile library. It can read almost all. It supports almost all the raster data formats available. So right. So so these are the advantages of using GDAL. So it is free and open source. So you need not pay anything for using it. It supports over 80 plus image formats and map projections. It has command line as well as C, C++, Python, R and Java APIs. So if you are not comfortable using programming, even it is for non-programmers as well. So it provides a command line interface as well. So with that command line interface also, you can automate many of your tasks. It is used extensively by the world's large geospatial data services. Most of the geospatial data services on the web also, they are on the backend using GDAL. So plus it includes extensive support for vector as well. So it supports both raster as well as vector data sets. So now if we see GDAL raster data model, so how raster data is represented in GDAL. So if you see in GDAL, the raster, so irrespective of the underlying format, like if the image is in BIL, PSQ or TIFF, if irrespective of any format, so once you read an image using GDAL, so the entire image will be represented as something called data set. So the so irrespective of the format, so underlined, so the details of the format will be taken care by the driver for that particular format, but to the user or the programmer, it will be represented as something, an abstract data model called data set. So the data set will in turn will have multiple bands and bands plus some maybe projection and transformation information associated with that image to map or to draw the image on the map. Right. So anytime you read a image using GDAL, you will be getting a data set. So and the data set will in turn will have multiple bands, and every band will have the data, and it might have some overview bands or some other metadata related to that image. So this is the coordinate system of an image. So any pixel on the image is referred by its row number and column number, as we have, because the image is represented as two-dimensional matrix, 2D or two-dimensional array. So any pixel on the image is referred, or you can index any pixel by using its row number and column number. This is on the image coordinate system. But this particular image might be representing some area on the Earth's surface, right? So then we need to attach latitude and longitude to that image. Also, suppose if you are using some projected coordinate system like UTM, so same thing now, from this we need to convert it to the latitude and longitudes. So with every pixel with every image, with every pixel, affine transformation information will be attached to the image. With the help of this affine transformation image, we can convert any pixel's location from image coordinate system, from the row number or line number and pixel number to the its latitude and longitude on the Earth's surface. Right, so these are the six elements of the affine transformation. So GT0 is called the x coordinate of the upper left corner. So 0 pixels latitude, and similar way this GT1 represents the pixel resolution in x x direction. Similar way, then rotation, if the north is up directly in your image, then it's this, you will see this numbers as 0. If the image is rotated, then it may show some number. Similar way, y coordinate of the upper left corner, then the column rotation, then maybe the resolution in the y direction. So these are so now after this, let us see how do we use this JDAL library. So if you have a local installation of Python, then you need to install JDAL on your system. Like then if you are using Anaconda, then you can just go Conda install JDAL, or otherwise through pip also you can install. Anyway, if you are using Google Colab, so by default in Google Colab, JDAL is already pre-installed. So you need not install anything, just you need to import the library. So actually I have stored all of the data which I will be using for demonstration in my Google Drive. So actually yesterday also some students were asking how do we access Google Drive from the Google Colab. I will be just showing it, thus you can follow it. So once this is connected, actually on this the left side you will see the files icon. So if you click here, and here you will see a logo of or icon for the drive or mount drive. So you can just click, if you click on this part, it inserts a piece of code in your notebook, like from google.colab import drive and drive.mount. Now next you need to run this piece of code. So it says connect to Google Drive, provide your credentials, and your Google Drive gets attached. Right, so once it is done, you can just click on the refresh. Then you will see a folder called Drive and My Drive. So inside this, whatever folder you create in your Google Drive, all will be visible. Like I have stored all the data in the data folder. Inside this, all the data is available. Right now, once this all is done, now the core name of the core package for JDAL is OSGeo. So the OSGeo is the name of the package. Inside that, JDAL is the module. So first thing, before using JDAL, we must import it, because by by default Python interpreter doesn't have JDAL. So we need to import all the functionality of JDAL by calling this from OSGeo import JDAL. And there is another library called pprint. Actually, pprint is for like beautifying the print. Like sometimes if you just print some messages using simple print operator, it is not quite good readable. So pprint actually is pretty printing. So with that you can beautify your printing on the screen. So next time here I am importing a package called OS. OS provides the interface to the operating system. Like you can change your working directory and create new folders, and also there are multiple functions available in OS. So I am calling that, and next I am calling os.chdir. So with os.chdir is for changing the directory. So first I am changing my working directory to the directory where my data is available. If I don't do this, I need to type full path name of my file every time. So because of this, because I don't want to write the entire full name, full path name, so I am just changing my working directory to be the directory where actual data is available. So that's just I am checking os.change directory to content drive my drive inside the data. Right now, let's try to inspect an image. So here in this particular folder, I have an image named haridwar.tif. So that is an image captured by resource set 2 satellite of ISRO, and the sensor is used is LIS3. So this particular image contains 4 band: green, red, NIR and SWIR bands. And this particular image is a stacked image of 4 bands. So let's try to read this particular image, or first we'll just try to get some basic information about this particular image, like what is the width, height, and how many bands are available in that image, and so on. So for that, JIDAL has their function called info, right? So if you call jidal.info and pass it the name of file which you want to query about, and the format, like a format in which you want your output to specify in CSV file format, or maybe a JSON format. So JSON format is like a key value pair format, as we have discussed in dictionary. Right, so dictionary has two things. One is one key and value. So similar way, when you try to represent this information, like this says that in which format you want to represent the information about that particular image. So now we wanted to show it as JSON. So now if I just run this command jidal.info, jidal is not. So now if I just print output, sorry, out underscore put it is. So now here you can see that the whatever is printed on the console is not readable. It's not so well formatted to read out. So for that we have another package called pprint. So instead of direct calling basic print, you can just call pprint.pprint pretty printing. If I do, now you can see that it has nicely formatted the text. Now it is quite easily readable. Right, now this is the information about the image what we have read. So it says bands. This particular image has like band 1. It has a block size of 1151 cross 1. Color interpretation is as gray. Then the max pixel intensity is 315 min, and this is the metadata about that particular image. Similar with second band, third band, fourth band, and other, like this is the coordinate system projection information about that image, description, or even any metadata which the producer of the image has attached to that. These are the extents of the image, like these are the 4 corners of the image. So this geographical area is covered by this particular image. So this, by calling jidal.info, you can get a basic information about the image. Right, so this has given in a pprint. Now suppose the same thing if you want to do individual element wise. So actually there are 2 ways to do that. Either first you can call jidal.info. Now it has returned you a dictionary. So on the dictionary now you can index these key values. There is another way to extract the similar information. Right, so anyway, here we are first. Anyway, this is jidal already has been imported. We need not import. Then I am just importing the matplotlib.pyplot, whatever we have used yesterday. Then numpy and OSR. Actually right now it is not required. This also is not required. Now same thing, we will open the file. Actually here we have used the command line called jidal.info. Now we will be using some basic jidal APIs. So first I have created a variable called file underscore name. In that I have stored the name of file which I am going to read. Now suppose for reading the file, there is a function. So actually, as I have said that jidal or Python is case sensitive programming language. So you must take care of these cases, like jidal dot O is capital OP. So OP, and it lists all the commands, and I need to pass the name of file. Right, now if I see DS, now you can say that it says it has returned osgo.jidal.dataset. As we have said that irrespective of the underlying format, maybe TIFF or whatever it is there. So once you read the image with jidal, so jidal driver for that particular format will handle all the low level details, and the image will be represented as an dataset object to you. So in that dataset object you can call many more methods, right? So suppose if you want to get the list of files which are like in an image file might have some XML or some other associated file, one RRD file, there may be many more files. Now suppose if you want to fetch the list of all files which are attached to this file, then you can call the function get file list. It lists all the files Similarly, suppose if you want to know the width of your image, like how many pixels are there in x direction, so then you can call your ds is your data set, ds dot raster x size width, then with ds dot raster y size you can calculate the height. So 1151 115 115. Then suppose if you want to get the coordinate system, so then you can call ds dot get projection. It fetches you the projection information attached to that image. So this is the projection information. So this is geographic coordinate system. Then suppose if you want to fetch the geo transformation or affine transformation information attached to the image, because with the help of these coefficient you can convert from the image coordinate any pixels from image coordinate system to the real world coordinate systems. So these are those 6 elements. Like this is the longitude of x0, then resolution in x direction, rotation, then similarly resolution y0's latitude and rotation, and resolution in y direction. Right. So suppose if you want to calculate convert from image coordinate system to the real world coordinate system, then there is a function called apply geo transform. So GDAL dot apply geo transform, then you can pass it the first a geo transform 6 element GT list and your pixel number and line number. So this way you can calculate the real world coordinate of any pixel in your image. Like we are trying to convert the coordinates of upper left corner, upper right, lower left, lower right, and center. All 4 corners and the center. So these are the real world coordinates of the 4 corners of our image. So similarly, suppose if you want to fetch the metadata attached to your image, so then you can call the function ds.get metadata. So it fetches all the metadata attached to your image. So there is only single key attached there. It says area or point, whether the value which are seeing in a pixel it represents an area or point, right? So the pixel may represent some area or point, but it says an area. So what does it mean? It means this particular pixel represents an average of an area. It doesn't represent a point value. So then similarly you can calculate how many bands are there in your image, whether it's a single band image or multiple band image. Then you can call the function ds.raster count. It fetches you how many bands are available to your image. It says there are 4 bands in your image. Now, now these all whatever statistics was shown here, suppose if you wanted to calculate all these statistics, then you need to iterate over all these bands one by one. As we said that the data set in turn contains bands. Right, so here we are running a loop for I in range 1. Actually, generally in computer science, the indexes start with the number 0. But in case of GDAL, band number index starts not with 0, band number starts with 1. So if image has 4 bands, the band number starts from band 1, band 2, band 3. In GDAL's parlance, we don't call it band 0, band 1, band 2, and band 3. We call band 1, 2, 3, and 4. Right, so here we are running a loop from 1 to 5 maybe. Then first from the data set we need to fetch a particular band. Like a data set contains multiple bands, so now you need to fetch individual band. So how do we fetch the individual band? By calling this ds.get raster band, and it pass it an argument like which band number you want to fetch. Right, suppose if I want to fetch here band 1, so I am passing it a band value of 1. Then I am just trying to get the interpretation of the color, and I'm calculating the band size and what is the interpretation of that color, and if there are any overviews attached to that image, we are just trying to get that as well. So now it shows that here there are no overviews attached to any image. So this way, this is the basic thing. How do we get some basic information about our image using GDAL library? So this is, anyway, that same thing can be done using GDAL.info as well. Now we will go in the detail. Now we will see how do we fetch the actual data from the image and how do we visualize image, then how do we some basic analysis on that image. So this will go later. So first thing, anyway, before using an image, you need to first open it for reading. So GDAL.open, then pass it the name of the file. Right, now this way we have seen that how do we fetch bands. Anyway, suppose if you want to compute the statistics on every band of your image, so then you need to iterate over all the bands of your image, and on the band there is a function available called compute statistics, and you can pass it an argument called true or false. So this false or true means approximation okay, whether the approximation is okay for you. So if you pass approx okay equal to false, what happens? This statistics gets calculated on the overview or overview counts. But if you pass it the value as false, then the statistics will be calculated on the native pixels. So right here, just we are calculating the basic statistics for all the bands. Like here, say band 1 has minimum pixel intensity 82, max 315. This is the mean value, and this is the standard deviation among the pixels. Right. So anyway, this may not be useful now. So first thing you need to remember, just jidal.open. It returns us a data set. So in the data set in turn will have multiple bands. Now we need to fetch a particular band from the image. Now we have the entire data set containing all the 4 bands. Now suppose if you want to fetch band 1 from our image, then on the data set there is a function available called get raster band. So if you call this function on the dataset dot get raster band and pass it an argument band number, which band number we want to fetch. So then it will return us an object called band. Now as we have said that band will contain image data, actual that matrix, or it may have some associated information like some overview counts, interpretations of that color and so on. Now suppose if you are interested, now suppose if you want to fetch the data from that array, like what are the pixel intensities in that band. So in that band there is another function called read as array. So if you call band dot read as array, so this returns us an numpy array. So because now we are just trying to read a single band, so it returns just a 2-dimensional array. So if I see this data equal to band dot read as array. If I call, so it fetches the actual data from my band 1. Now if I just print this, now you can see that this is a 2-dimensional matrix, right? So this actual image is ultimately represented in computer's memory like this. Computer sees our image like these numbers, right? So actually all the values are not shown here because of the performance reason. What NumPy does, NumPy doesn't show all values, it just shows the truncated values. Now there are options also. Suppose if you want to see the all the pixel values together, so in the NumPy you need to set some option with that, then you can see also. So this way you can see the data. So this is we have seen. Now suppose if you want to visualize how this particular band looks like, right? So as we have seen yesterday, there was a function in matplotlib that is called plt.imshow, right? So here first I have created a figure of some specified size, maybe 10 by 10, because our image is a square image. So I have created a figure. Then in that I have called the function plt.imshow. To this I am passing the data, right? Then color map gray if I do. So this is our Haridwar image band 1. This is the band 1 of our image. Similar way, suppose if you want to fetch another band, you can specify it band as band 2 and call this. This is band 2. Actually all are looking similar, but there is slight difference if you see closely. Now suppose if you want to visualize all 4 bands together, as we have discussed yesterday, in matplotlib figure we can create subplots, right? So here we are creating with plt.subplot one. Inside a figure we are creating a grid 2 by 4, 2 by 2, 2 cross 2 subplots, or 4 subplots inside that, and in every subplot we are plotting individual band, like we are iterating over for 1 to 4, when band 1, band 2, band 3, band 4. This way you can, suppose if you want to visualize all 4 bands together in different subplots, now you can see that these are all 4 bands you can visualize this way. Like there is subtle difference between these bands. Like these areas are quite dark in this band, and these areas have become brighter in these bands. So if you know basics of remote sensing, you must be able to differentiate between these bands. Right, this was the when we were visualizing single band images, right? So though there are many possible combinations of wavelength bands, generally for visualizing a multi-band raster we select, because the satellite image might have multiple bands, like it may have NIR, SWIR, red, green, blue, or red edge. There will be multiple bands. But for visualization we need to select out of these bands, any 3 bands can be selected for creating a composite or or composite image, right? So out of these bands, we can select any three bands to be represented as red, green, or blue. So once we combine these red, green, and blue colors, then the generated image is called a false color composite. Like, so here you can say that we have some seven bands in or six bands in our source image. Now out of these six bands, we can select any band to be represented and as blue in our RGB composite, and any other second band also we can select second any out of these six remaining five, we can select any other band to be represented as green, and the third band any of this can be represented as red. So we can select any combination of these bands to be selected as green, blue, or red. So the after combining these three bands together, whatever image we get, that is called a composite image or false color composite of that. So depending on like which feature you are more interested in, so depending on that, you generally people in the remote sensing, they select the band combination accordingly for highlighting this particular feature which we are interested in. So the image whatever we have here, that Haridwar.tif, this particular image has four bands. So these are the four bands in that. So one is there is no blue band. Actually, red, green, red, NIR, and SWIR. These four bands are available in our particular image. So there are some standard ways for selecting this band combination for RGB. So there is one standard false. That is one thing. One combination is called standard or traditional false color composite. So in that, what do we do? The near infrared NIR band is represented as red, and red is represented as green, and green band is represented as blue. So that is called a false. That is called the false color composite. So this is a traditional band combination that is useful in seeing changes in the plant's health. So if you are interested in seeing the health of plant, then you can use this combination with this standard false color composite. You see the healthy plants as dark red color. So NIR you represent as red, red as green, and green as blue. So and then similarly there are other combinations. Suppose if you are interested in seeing the floods or newly burnt area like forest fires and other natural disasters take place. So suppose if you are interested in seeing floods or burnt area, then you can use this combination. Shortwave infrared SWIR you can use in the red band, NIR as green, and green as blue. So if you use this band combination, you can easily identify the flooded areas and maybe newly burnt areas. Then there are other combinations, like if you see blue as red and there are two SWIR 1 and SWIR 2 are there. If you use them for green and blue, you can see this to differentiate between snow, ice, and cloud. Actually, if you see in the natural color composite or in simple RGB, then it is difficult to identify snow, ice, and clouds. If you use this band combination, it becomes easy. In similar way, you can use thermal infrared to show the tones of gray to illustrate temperature by different different shades of grayscale. You can differentiate the temperatures. So now let us see how do we create some false color composites. Now our Haridwar.tif image has four bands. Now we will select a combination of these three bands to create, and then see that the same image looks different in different band combinations. Now let us see how do we create a standard false color composite. So in this, what we will do, we will create a near infrared, whatever near infrared band is there, that we will store in the red, and red in the green, and green will represent as blue. Right, as you have seen that. Now first, same thing is our DS will represent our, in DS we are calling jidal.open and passing it the name of the file. So now we have a DS available to this. Now as we said that from the data set in turn will contain multiple bands. Now suppose if you are interested in just fetching a single band, so then you can call ds.getRaster band. On that band, then you can call read as array function. But there is an other shorthand. Directly on the DS, you can specify, you can call the function read as array as well. And you can pass it the name of another argument called band list. Band list specifies which all bands you want to read. Right? So DS, if you call ds.read array, and it pass like there are four bands, but I just want to read any three bands. So three bands which I want to read band 3, band 2, and band 1. So band 3 represents NIR. So I want to use it for red. Band 2 represents green, red, sorry, band 2 represents red, and band 1 represents a green color. So I'm just fetching three bands, NIR, red, and green. So this all the data is fetched in my multi-data variable. So if I see the shape of this multi-data, it says 3 cross 1151 cross 1151. So there are there are three 1151 cross 1151 two-dimensional, or this is a 3D array. Now, because this is in the format is called CWH, channel width and height. But actually, as we discussed yesterday, matplotlib, whenever you are plotting a multi-band image in matplotlib, we need to convert it to the format from CWH to HWC. So for that, we are just calling a function called np.transpose. With that, we are just transposing its axis. So if I call multi-data np.transpose, now if I see the shape of this multi-data, you can see now the shape has changed from 1153 cross 1151 cross 1151 to 1151 cross 1151 cross 3. So from CWH to HWC format, we have transposed our data. Now for plotting the image, now once the data is in this HWC format, then now we need to call just the function plt.imshow. So whenever you pass data like this to plt.imshow assumes that whatever data you are passing, first band is red, second band is green, and third band is blue. So if we see here, now here you can see that this is a standard false color composite of Haridwar area of this particular list 3 image. Right, so you must be able to, if initially actually it might be confusing to you. So here you can see that we have just read NIR, red and green, 3 bands from the original raster image. But while displaying the image, what we are doing, this NIR is being represented as red, and red NIR is being represented as red, and red is being represented by green, and green color, whatever is green reflected, green pixel intensities are there in our original image, those are being represented as a blue color, because when we have to create a composite for visualization actually we need 3 colors, R, G and B. So in R you can put any band, any band you can put, like whatever, suppose our satellite image has 7 bands. So out of these 7 bands, any of the band we can put in the red for visualization. Similarly, any second band we can pick up from those 7 bands and put in the G band. And similarly, third band we can push and select and put it into the B for visualization. So similarly, what we have done here, NIR is going to the red is going to green, and green is going to blue. So this way we can create, this is called what is called a standard false color composite. This is just used for monitoring the health of the plant. So here you can see that all which are you seeing in the red, that is all healthy vegetation. Similarly, we can create another combination, like here what we are doing here, SWIR we are representing as red, and NIR as green, and green as blue. So fourth band is our SWIR band. So that will be going to the red, and third band is our NIR, and first is blue. 2 actually now we have skipped here. So now image is same. Now this image we are visualizing with different band combination. Right, so this is another. So similar ways we can have any combination of these images. So now these same images, but we have selected different bands for visualization. Now you can see that 3 different false color composites of the same image by different band combinations. Now suppose now there is an option, like suppose if your image is very huge image, and suppose if you have limited memory and you want to read certain subset of your image, so then you can read the partial data also. So that you can call the same function band.read as array. Here you can specify like from which pixel number and line number you want to read, and how many pixels you want to read. So by default, if you don't pass any argument to read as array function, it reads your entire image. But if you pass these arguments to the read as array function, you can read the partial image as well. So here you can see that think this got terminated. Just a minute. I will just call this once again. Oh, the drive did not get initialized. I have not changed my working directory because it was not able to find the file. So this way we can read partial. So instead of reading the entire image, now we have just read the this small portion subset of our image. So we will see this later anyway, not so important writing. Now second thing comes, like once you have multiple images with you, and suppose now second part we will see how do we write an image. So this is all about reading. Now let's see how do we write image. Now suppose if you have an image and you have done some processing on your image, maybe done calculated some index or done some edge detection or some processing you have done on image, and suppose you want to write it back to the image. Actually there are two methods to write an image using GDAL. One is called create copy and another is create. So create copy is useful when you have already some data available to you in GOT format or maybe some standard format, only you have read that and you have done some processing and you just want to write the same image back, like the processed value, but all your you want all your transformation, number of bands and other things to be same as your source image. So in that case create copy is useful. But create is useful when you have data in maybe different format. You have stored data in say CSV format. From that you want to read your data and you want to write. So in that case you can use create method. So first we will use create copy and then see how to use create. So first I have created a variable called file format. File format I am specifying here which format I want to. So actually for every format there will be a different driver in GDAL and every driver has a short name. Actually for that you need to refer to this link here. So here it gives the shorthand name for all different formats. Like suppose if you want to write an image using GeoTIFF, then the short form is GTIFF. If you want to write in CIOS image, the format short name the format is CIOS. Pole gas data CPG, CTG. So these are the short names. So you need to search on this website jidal.org drivers raster. So here from here you need to get the short name for your driver. So because I wanted to store the data in GTIFF format, so I have created GTIFF. So first thing, for writing an image you need to create a driver. So first you need to create a driver for that particular format. That can be created by using jidal.get driver by name and pass it the name of the shorthand name of the format for which you want to create a driver. So once a driver is created, you can call it like driver short name, long name, anything, metadata, and all thing you can give. Now here, I have already an image of list stream is the same thing. I am storing that. Now in this image, I will do some processing in this image, and I just wanted to save the output and in some different file, maybe output raster1.tiff. Right. So for using create copy method, first I need to open this file because I want to do some processing on this source image. So I am just opening this file for reading. Then later on I am creating a driver for handling my format because I want to store the data in the GeoTIFF format. Then for create copy, there is a function on the driver. I need to call the function driver dot create copy, and to this I need to pass the destination file name in which I want to write the data, and the source data set from which I want to copy. Like if I call this driver dot create copy, this particular driver will copy everything from the source file, maybe all the bands information, projection information, all the overview counts, everything it will copy from the source data set. Now I am just reading this source from the source data set data. Now and I am just inverting the data. Here my processing is like I am just inverting, like the areas which, like this is like developing a negative. Like all the inverting means we are just converting ones to zeros and zeros to ones. So areas which were darker, they will become now bright, and areas which were bright will become dark. So this is something like, so I'll call inverted data np.invert. Now if I see these two images, I have done some basic processing on my image. So like this was this was our original image. This is the inverted image. Here you can see the areas which were dark have become bright in this particular area. So this is something like developing an image. Now once you have done processing on the data, then you can call on your destination data set, call get raster band 1. Then while reading data, there was a function was read as array and writing write array. So if you do write array, and then finally actually you need to call this function out dot flush cache and delete ds. So this saves. Now if I see in my drive and data, a file with op underscore raster1.tif must have been created. So here you can see that op raster1.tif has been created. Now if I just want to check whether the file is, or I can just delete this as well. And if I run it once again, actually I have just deleted this. I need to run this entire portion once again. Now you see how op underscore raster1.tif must be get created here. Now you can see that op raster1.tif got created once again. So now suppose if you want to see this image, you can just check whether the output is correct or not. So this way you can see that whatever we have seen the output here, the same image got written here. Right, now let us see some basic, these are the basic things where we can, there is another method called create. Actually because of limitation of time I will not be able to discuss that. So now let us see some basic raster data processing. Like this one simple processing we have seen. Now there is something called mosaicing. So mosaic is a combination or merge of two or more images. Like suppose if we have two spatially you have two different images covering the different geographic area, and suppose if you want to create a seamless mosaic, like suppose if you want to create a big image by combining these images which are covering different different geospatial area. So that is called what is called mosaicing. A satellite image mosaic is you can say a composition of several satellite images to create a single seamless larger image. So merging an individual image into a bigger image mosaic is called image mosaicing. Like here we can see that these are 4 images covering different spatial extents, and by mosaicing we can create a bigger seamless image. But what might happen, there may be some areas may be overlapping. So mosaicing is a complex process, right? So if the images are not at all overlapping, then it is quite simple. But even then you need to know that where this will fit and where this image it will fit. But there are certain issues, like if some tiles may be overlapping, so then you need to tackle how to solve this overlapping areas. What value to show at these overlapping areas and all. Actually by default GDAL shows the last image on that. Actually then there are other options available for mosaicing where you can like do feathering, calculate min, max, median of the overlapping pixel and so on. But for the simple thing, we will see that the last image which comes in the stack will only, the values from that image only will be taken for the overlapping area. So here we have 4 images. Now we will just try to create the mosaic of these images. Now I have stored the names of file in a list, all those names of 4 files. Now in this loop, I am going over all in this entire list and opening all these files one by one for reading, and the these dataset I am appending to something called a DSS list. And let's visualize these four images together. So these are the four images from which we want to suppose create a mosaic. Actually, these four images are not overlapping anywhere, but even if they are overlapping, but in that case, Jidal, what it does, it takes the last image wherever images are overlapping, the values from the last image in that stack. So for mosaicing images, there is an utility called warp. So if you call Jidal.warp, so it can be used. It is a very versatile utility. You can use it for creating mosaics or maybe reprojecting the image and so on. So Jidal.warp, to this you need to pass the name of a destination image, like where in by which name you want to store your mosaic image. So right now there may not be any mosaic.tif, I hope, in this. So there is there. I will just delete this. Right, Jidal.warp, and you want this is destination file name. Then another argument you need to pass it the names of files, a list of file names which you want to create mosaic of, and then format, in which format you want to store. And there are many more options which you can search for Jidal.warp option and you will get the option. So if you call just this function Jidal.warp mosaic.tif, so then it creates a mosaic and creates a data set as well. So if you read that data set dot read as if you do, and a mosaic image.tif also has been created, and a mosaic of these images. Now here you can see that all these four pieces were there, and from these four pieces we are able to create a seamless bigger mosaic, right? So this way, by using Jidal.warp, you can create a mosaic. Now let us see some other analysis on the image, something called local analysis. So local analysis it is like suppose if you want to perform certain operation in every pixel on your image, that is called a local operation. So local analysis work on two or more arrays that are of the same size, and an algebraic equation is applied to each set of pixels pixel locations, right? Like one common task using multispectral imagery is to compute various indices for the task, such as maybe distinguishing between burned and urban area, burned and unburned area, or maybe vegetation and non-vegetation, or maybe identifying waters, right? So local analysis means the analysis which is, or the algebraic operation this which is done on the every pixel on our image. So this is called local analysis, right? So like here, assume that we have two images and we want to add the pixel values of these images. So what here we are doing, we are doing the element wise sum of, or pixel wise sum of all, pixel wise sum for the entire image, like 1 and 1 plus 1 2. So every pixel we are doing the summation by using the another image. So now let us see how do we do this in using NumPy. Now suppose if you want to calculate NDVI, that is called normalized difference vegetation index. So this will have the values from range minus to 1, minus 1 to plus 1. So the pixels which are vegetation will be showing the values above 0, like maybe 0.3, 0.4 and 0.5. So with this way, automatically you can identify the vegetation pixels. So here, as we have said that band 2 represents in our actual, now suppose if you download the data from Bhuvan, so you will get the images, different files for the different bands. Right, as we have said that band 2 is green, band 3 is red, band 4 is NIR, and band 5 is SWIR. So I am just calling these by variable names, like band 2 image in gas green image, band 2. So now so the formula for the NDVI is NIR minus red. So pixel intensity is NIR minus red divided by NIR plus red, right? So this will be done for the every pixel in our entire image. So now first I am reading the red image. So Jidal.open red image, similar way NIR image. And then once the image is red, now suppose if you want to fetch the particular band, so by calling get raster band and passing it the band number, we get the values the similar way NIR. Now because these values are in unsigned integer 6, so suppose if you do a negation or a subtraction of two unsigned integers and if the result is negative, then it becomes a overflow condition. So to handle this overflow condition, what we are doing first, I'm converting these unsigned integers to floating point numbers, so that so either I can convert them to the signed integer itself, but for easiness I'm just converting them to the floating point number. Anyway, it will consume more memory, but for simplicity I'm just converting them to the floating point number. So a red equal to red band dot read as array, I'm just multiplying by 1.0 maybe, so that converts it into the floating point numbers. Now I need to because now I have two numpy arrays, red and NIR. Now I want to do element wise, I want to apply this formula. So I will write NIR minus red divided by NIR plus red. With that I get NDVI. So now if I see this NDVI map, now you can see that, see these all areas which are in bright, they have some vegetation. You can use some different color map also for visualization, like in the Matplotlib's website these are available. By default you can calculate. So the areas which are brighter, or you can say there's higher value, like these are all vegetations. And similar way, suppose if you want to identify water pixels in your image. So for identifying water pixels, there is another index called NDWI, or normalized difference water index. So the formula for that is green minus NIR divided by green plus NIR. Now the same thing doing again here. We are reading this green image and NIR image, and we are putting the formula NDWI equal to green minus NIR divided by green plus NIR. And if I run this, you can see now that all the pixels which has water are now showing in the bright color, right? So this way we automatically through a computer we can identify. Anyway, visually it is very easy to identify because the water bodies, water pixels, but for computer it is very difficult to do that. Suppose if this is the NDWI can be used for identifying water pixels automatically by your program, right? Now suppose if you want to mask out all the non-water pixels, right? So as we discussed yesterday, there is a function called np.var. Like suppose if you assume that values above 0.1 are representing what water pixels. So what I can do here, np.var ndwi is greater than 0.01, I will assign them the value 1, and all values which are less than 0.01 will become 0. So with that we can mask all the non-water pixels. Now if we see this particular image, now you can see that only water pixels has come up. So this way you can mask all other mask your image. Now suppose if we are just interested in identifying how many pixels contain water. So this way you can mask all other pixels and get the count of how many pixels are there. So with this we may be able to calculate the surface area of the water, like how many water pixels are there by counting them and multiplying them what is the area pixel cover. So this way we can say that this is the extent of water in this particular image. So with that these basic things, we come to the end of today's lecture. So I will just briefly summarize what all we have discussed. Basically, we used a library called GDAL, a Geospatial Data Abstraction Library. That is one of the most versatile libraries for raster and vector data operations. So basic thing, what you need to remember, that first thing, irrespective of the format in which the raster data is stored, once you read or write an image using GDAL, GDAL's raster data model is that entire raster data will be represented as a data set. So all the underlying details of the format will be hidden from the user, and an abstract model of the image as a data set will be represented to the user. That data set in turn will have some bands and the associated information. Like once you read an image by calling GDAL.open and passing it the name of the file, you get a data set. On the data set, now you can call, suppose if you are you can fetch individual bands from that data set by calling dataset dot get raster band. Once you have fetched a raster band, now then you can get the actual data or numpy array from that image by calling read as array function. So once you call read as array functions, you can get the actual data. Then the second part, we say how do we visualize a single band image. So for that, Matplotlib has a function called imshow, plt.imshow, and pass it a one-dimensional array. It gets visualized, two-dimensional array, sorry, then you get an image. For visualizing an multi-band image, as we said that we need three colors R, G, and B for visualizing visualizing image. But NumPy or Matplotlib expects the data to be in HWC format. So, but JIDAL is giving us in CWH format. By just calling the transpose function, we are converting it from the CWH to HWC format. So once it is done, then we can select any, like suppose if our image has 5 or 6 bands. So out of that 5 and 6 band, we can choose any band to be represented as red, green, or blue. So by choosing different band combination, we can visualize different features, or suppose we can visualize an image, and depending on our features of interest, we can select these combinations for creating an RGB image. Then we saw how do we create a mosaic using jidal.warp, and then finally we saw how do we do some local analysis like calculating NDVI, NDWI, or any other index or any operation which we can apply. This needs to be applied on every pixel on our image. So thank you very much. If you have any questions, you are welcome to post them on the chat box. So we'll be back after 5 minutes. Thank you very much.